So firstly, let me start by saying thank you for giving up your time to join this in your morning or afternoon. We are going to give a very, very high level overview of centrifugal pump testing. Now, we could talk for an entire week on this topic. So given the 50 minutes or so we have, this is going to be a very high level session. We're going to touch on a lot of topics very, very, very briefly, try and give a very broad overview. Any areas you want more detail on, feel free to reach out to any of us. We're all contactable on LinkedIn. But any questions relating to this presentation, please drop them in the chat at any point during the session. We will get to them at the end. There is enough time that we'll make sure we close out any of the main questions. Okay, so we're just going to run through who's presenting today, and then we're going to talk through a very, very small overview of Trillium, and then we're going to get into the agenda for the session. So the three people that are going to be presenting today, firstly, is the name that's potentially most familiar to people joining in Simon Bradshaw. Simon has a wealth of experience. He's got over 3 decades in the pump industry. He's managed to secure numerous patents, including one with us recently, and he spent an extensive amount of time at Circor, ITT, Weir Pumps, and Sulzer. Simon, for those of you that aren't already, is very prolific in terms of his content on LinkedIn, and I would strongly recommend to any of you to make sure you're following him on Pumping Corner going forward. Massimiliano is our head of both research and development and project engineering. So he has to help us come up with our new ideas and also execute on them. So he's one of the busiest people in our company. He's got over nearly 3 decades in the industry and has been with Trillium at our La Spezia site for around 10 years. And then last and absolutely least is myself. I've got just over 16 years in the pump industry, spread across one other pump company and Trillium, where I've been for around 3 years as the product director. Okay, so a very high level is just a couple of slides to explain who we are. So the try in our name was always around the 3 pillars of our business. This is pumps, valves, and services. I'm not going to spend too much time talking about the valve side or the service side here. Just give a very quick overview of the main pump brands. We also have a steam turbine brand, but this is a very niche part of our business. And the main piece, and what we're certainly focused on today, is the pump side. So the brands, I hope the brands are ones you're mostly familiar with, but just as a quick recap for any you may not be, all these brands have been standalone businesses and have operated across a range of markets. But just to touch on what their real strengths are and their key focus, Begemann and Gabionetta are very much an oil and gas business. They're now centered out of our Milan facility in Italy. And then we have Termomeccanica as our site in La Spezia, again about a 3-hour drive from the Milan site. That's our engineered pump solution business. This is our very high energy, very complex package, both for service, upgrades, re-rates, and original equipment. One of the largest test shops in all of Europe. With the Gabionetta site, it's slightly different. It's a newer facility, one of the newest pump manufacturing sites within Europe, being purpose-built in 2016. So all about different strengths for different markets, different key customers. Then as we get into the more industrial brands in Wemco and WSP, they are predominantly sold in the Americas, although we do have installations worldwide. And the Rotorjet is a very niche product that is sold at multiple sites. That's a product line that you may be less familiar with, and we can link to a separate webinar on that. This is a very low flow, high head design that is really underutilized in the industry, has a huge amount of advantages, and is our equivalent to the OH6. Can be used in place of a recip or a very high-speed pump that would otherwise require a gearbox. So I'm not going to talk to this slide in too much detail as we've touched on the key points. The only point I'd like to make is you can see here, this is the formation of our 3 main pump brands. And you see that it's given us around 3 centuries of experience. That's from past installs, from engineering experience, patents, design IP. And one of the things that we're very focused on at the minute is a big push in investment, R&D, new product introduction. So it's building on the heritage we have from these 3 businesses and making sure we're expanding it into the future. And there's a lot of things that we're going to be sharing over the rest of this year. So Yes, we understand that Trillium's a new name from 2019, but we're hoping just to highlight with this slide that we have been around for a lot longer in terms of the experience with our brands behind that. As mentioned, you will typically see that we have experience across every main pump type. The only type on here that we don't supply in terms of conventional API designation is the OH6. So we have our alternate, which is the rotorjet pump we briefly discussed. Again, comes with a lot of advantages, comes with some trade-offs. It's not always right to replace an OH6, but it does have some installations and some opportunities where there is no other equal. And it's one of our jobs to do more of a role in promoting that product line for those services. We also have some very unique high capacity, low head concrete volute pumps that are on here that will go to almost 100,000 meters cubed. So huge range of product, and it's where those brands are coming together as a complementary mix and are not just a series of standalone businesses anymore going forward. Okay, so with that said, the agenda for today and what we're going to try and cover at a very high level, we're going to cover why testing matters. So roughly, depending on the estimates you read, between 10 and 15% of world energy is going into pumps. So globally, it's critically important that the pumps in the field are doing what they were specified to do. Testing validates that. Testing is there to make sure what was sold is what's delivered. When these packages are installed, there are so many complexities from the entire system. The one thing that pump testing does is remove a variable and allows us to say we have confidence in what the pump unit's doing. We're then going to talk about what standards exist in the industry, what the test tolerances are and why we have them. Massimiliano is then going to walk us through the different types of pump test. There are many more than we're going to cover in this session, but hopefully it gives you a good high-level grounding in the common types, what the difference between a performance test and a mechanical run test is, etc. We're then going to talk a little bit about the different types of test standards. Simon, who's on the API committee, is then going to talk us through the differences between API and Hydraulic Institute. We're then also going to talk about tolerances, guarantees, acceptance criteria. Very underappreciated section, because we're going to try and highlight where two pumps that look the same at a proposal level can be drastically different in the field. And we're also going to quantify the cost that can actually incur in the real world. These decisions cost millions and millions of pounds a year to end users. And it's a hugely underappreciated area, and it's something that I think is generally misunderstood within our industry. We're going to then talk very briefly about how do we handle outliers. So things like, what can testing not tell us? What is testing good at identifying? Is more testing always better? What do you do when it's an oil and gas application and you're pumping propane, ethane, things that bear no resemblance to water? Also, we can talk about high temperature testing, what you do for test setup, what instrumentation we have, and just a quick overview of the differences between factory and field testing. We finally got one slide to say, if you're witnessing a pump test, what are some of the key things you should watch out for? And then a very quick wrap up at the end, and we will then make time for the Q&A section. Okay, and just a reminder, at any point, please drop questions in the chat. If we have time, we'll address them as they come in. If not, we'll come to them at the end. Okay, so why testing matters? So as mentioned, testing is there to ensure the equipment is fit for purpose. Catching and rectifying issues at any stage is expensive. Doing it in the pump OEM's manufacturing facility is 1/10 of the cost of rectifying these issues at site. And above all else, we need to prove that the pump is a known quantity, so that when it goes into the system that has elevation changes that aren't quite to plan, it has a different pipework routing because something changed during the construction process. You have every valve, every elbow, every bit of pipe, every pressure loss assumption that's been made. You have all these unknowns and slight uncertainties going into the full system. We need to know that the pump is a known quantity, and that's what testing is there for. Again, we'll talk about the different types and how much of that you can prove in the test shop, but at a high level, this is why we are doing it. Fixing mistakes in the field is phenomenally expensive. Key thing that we want to stress throughout is more testing does not equal a better outcome. If you x-ray a leg that you know isn't broken, you haven't learned anything. And pump testing is no different. Excessive testing with no benefit should be stamped out at all costs. It carries lead time, it carries cost, and it carries risk. As I mentioned, we have one of the newest facilities in Europe for this. We have a dedicated test loop. Testing is still very labor intensive. It's still very energy intensive, and it's still very time intensive. And those are things you cannot get away from because you are trying to replicate site conditions on a pump test rig. We also have to recognize there's risk. So if we look on the next chart, so what this is trying to show in red, I'll not spend too much time. So this is increasing flow and increasing bearing load. So all it's showing is as we move the flow back away from BEP, where the load is at the lowest, and we come towards a zero flow, or what we'll typically call closed valve, this is where the pump has no flow, and all the energy from the motor is going straight into heating the fluid. What comes with that is a drastic increase in bearing load. I won't go into too much detail on this, but essentially, if you have designed a unit to operate on a light hydrocarbon, that bearing load will be much, much lower than it will ever see operating on water. So you can introduce risk by going back here. And even on high energy pumps that are designed for water, running there at any length of time increases risk, increases the probability of failure. And just generally, the more stop-starts you have on the pump, the more opportunity there is for something to go wrong. And we need to be aware of that when we're specifying tests. We also need to understand the limitations. We need to understand what it's not going to tell us. So particularly for differences in fluid, as we're going to go into later, and making sure as we talk about, there are a lot of conflicting standards. Picking the right one and selecting the right set of tolerances from that standard is not easy. And it's something that has to be done in collaboration with the pump OEM, really at the early stages of the project. So in terms of the key standards we'll talk to today, we're really going to talk to two. So we're really going to talk to API 610 and Hydraulic Institute 14.6. Key differences here, API 610 is, for those who aren't familiar, American Petroleum Institute. So as you can understand, it's very focused on oil and gas. It is not a testing standard. It is a complete standard for manufacturing centrifugal pumps. This is good and bad. This means it's much more prescriptive, which from 80-90% of applications is a very good thing. It's straightforward, it's clear, the guidance is in place. The downside that comes with that is there's less flexibility, or you have to know where you need to deviate from the spec for higher energy, more complicated, where you need tighter test tolerances. Hydraulic Institute 14.6 is a testing standard. Now, the upside here is it has a much broader range of acceptance criteria. But as any of you know that have custom equipment, whether it's a custom PC or a hi-fi, yes, having more options to tune things can be advantageous, but it can also give you the opportunity to get yourself in trouble. So we'll talk about the differences between these, and we'll show just the wide range that Hydraulic Institute allows. And even why selecting a higher test tolerance is not always a better thing for the total system, which is a very, very key part and something that's very often overlooked. So if we start with why we have test tolerances, so why are we not just saying there's a sold curve, match the sold curve, there shouldn't be any discussion, we don't need to overcomplicate it. We want to stress that pumps are not digital machines. You do not get the same exact output every time that you put in. If we just give one example from a casting perspective, so yes, there are many improvements in castings. There are many things we can do to remove uncertainty, but we have to all acknowledge the reality. You are still pouring molten metal into a mold. The molds move, they cool differently. You do not get the exact same casting surface finish, quality, dimensions every single time. The same drawing to the same pattern equipment at the same foundry, poured within the same week, will give you a different result. We're not talking a huge difference, but we are talking a small imperfection. And all these imperfections and tolerance stack on your running clearances on your wearings, they add up. And this means you are going to see some variation. That variation is normal. There are a lot of things that we can do as a pump OEM to reduce that variation, and we'll talk about some of those later. But this is why we need different test standards, because reducing that variation adds cost and more and further checks to the system. We want to make sure we're only doing that where it's appropriate and correct. So, for example, if we were trying to drive higher efficiency, we could put tighter controls on inspection, we could polish components, but ultimately it may force us down the road of a new design. So the test standards that are picked are of critical importance. Okay, so very quickly, I'll just set up for Massimiliano. So if we talk about the types of pump testing that we have. So what we really want to cover here is just what we're looking at as a performance curve. So what are we trying to get? So you have flow horizontally and pressure or head on the vertical axis. What we're trying to do on a performance test is sweep through an agreed number of points along this curve to prove out that we are hitting the required flow and head. That's the number one check we're trying to do. We're then also trying to record the power as we go through the flow range and understand, is the efficiency in line with what was sold? Is the motor going to be able to power it at site if there's a difference in product or specific gravity? And then we won't always test for this, but then when it's specified, we'll do an NPSH test, which Massimiliano will walk through shortly, and is about proving the level of suction pressure that the pump needs to operate. So Massimiliano is going to take us through these four, but just to give a very quick overview, we have hydrostatic testing, which is the first check that's done in the manufacturing program. This is all about making sure that we'll essentially pump the case full of water, increase the pressure to about 1.5 times the load it would see in the field, and make sure the casing and bolting is performing adequately. Performance testing is, as we've just discussed, are we hitting the performance points in terms of flow, head, power, and efficiency? Following on from that, you could have NPSH testing where it's required. Typically, you'll only look at doing that testing if there is a very tight or very limited suction pressure available. And finally, mechanical run, which is basically an extended performance test that is making sure your temperatures are stable. And with that, I'll hand over to Massimiliano and let him walk through in a bit more detail.
Thank you, Sam, and again, welcome to everybody. I continue the introduction of different types of pump testing, starting with the hydrostatic testing, that is the pressure test that is used to verify the structural integrity of the pressure-containing components. The typical example is the pump casing, in order to be sure that they are able to withstand the maximum allowable working pressure. This kind of test is the standard duration is 30 minutes. The fluid that is used is typically clean water. And at the end of this time, basically no leaks and no permanent deformation are allowable by the test. Generally, as Sam already said, different standards define the hydrostatic test pressure in a different way. A couple of examples is HI 14.6 that define the hydrostatic test pressure as 1.3 times the design pressure. In a different way, API 610 standard define the hydrostatic test pressure as 1.5 the design pressure. Finally, there is a case that has to be considered. For example, a pump that is going to work in the plant with very light hydrocarbon. Generally, in the hydrostatic test, we introduce the wetting agent just to have an hydrostatic test that is as close as possible to the real condition, because the action of the wetting agents is to reduce the surface tension of the water, and so in some cases it is the test that the water is able to pass through the leaks, any micro leaks that you can have in the pressure containing parts, and so the test, the hydrostatic test, is close as much as possible to the real condition. This is something different, and we think that is something that we have to mention. Okay, please go. Okay, now we move to the performance testing. That is a critical requirement to verify that the pumps are completely in compliance with the contract requirement. And this testing is absolutely necessary to verify the performance in terms of flow rate, differential head, overall efficiency of the pump, and absorber power. Generally, we run this test across various flow points, and the scope is to describe as much as possible the curve in the proper way. We define the guarantee points as per contract requirements, and during this test, vibration is monitored at each point, and also other parameters, for example, bearing temperature. This is a special requirement by API. Finally, the point that will be deeply described later by Simon is that testing tolerance is a very, very important feature here, because it makes the difference. It is affecting the pass or fail decision for the test. Basically, the curve is the same, but considering different tolerance, you can have really the possibility to pass or fail the test according to the client requirement. Okay, we can move to the next one, that is the mechanical running test. That is a really critical performance evaluation process that is generally conducted before a pump is shipped to customer. It is necessary to verify the mechanical performance of the machine. This test, the standard duration is 4 hours, where continuous run at rated flow is required. But a very important point is that before running the 4 hours, the oil temperature has to be properly stabilized. Generally, the tracking of vibration, temperature, and lubrication and seals is required here. And again, this test is very, very useful to identify if any mechanical defect are here before ship the pump to the plant. A special case is the string test, where the scope of the test is enlarged. Basically, it is not limited to the centrifugal pumps only, but the scope cover all the equipment that are in the train. So the pump for sure, but we can have the driver, we can have the seal system installed, we can have lube oil when it is required, variable frequency driver, fluid coupling, we can have gearbox. Let's say all the components that are inside the train are properly tested in the string test. Okay. Okay, now we move to a very important test that is the verification of the NPSH. That is necessary to confirm net positive suction head that is required. One of the most visible effect of cavitation is the degradation of the performance due to the presence of the vapor phase that is inducted by cavitation. The definition of the required NPSH of a pump is the NPSH available that is able to drive the total head to be reduced generally by 3%. Due to the flow blockage from cavitation vapor in the impeller vanes. Basically, we have some nice picture that we take from a CFD simulation that we have run in our R&D department, where you can see the presence of the bubble in the veins. You can see in the top where the quantity of the bubble that are able to generate the 3% head drop, and in the bottom you have less quantity of vapor bubble, and here the drop is around 100%. 3% is the generally used criteria by the industry. It is an industry standard. It is not the only one, because as you already mentioned, we can refer to 1%, that is a different quantity of bubble, or 0%, or even also to incipient cavitation, that is the condition where bubble are almost not present. Basically, you have the veins that are completely clean. How this test is generally conducted in the test room? Basically, the industry standard is to run at constant flow rate. Let's say in the slide there is a picture that is from HA 9.6.1. Generally, this test is starting at 2 times the NPSH required, and basically you decrease the suction pressure until the cavitation is enough to degrade the pump head by 3%. So it is the 3% drop. Okay, we can move to the next one. Okay, now there is a quick overview of Trillium Flow Technology testing capabilities in Italy, that is Nova Milanese plant and La Spezia plant, and also in US, in Fresno, California. Starting from Nova Milanese, we have a test rig that is able to run machine up to a maximum test power of 8 megawatt and maximum test flow rate of 12,000 cubic meter per hour. The special feature of this test center is to have a lot of test loop, 13, and so to be able to quick change the setup of the test. And so basically we are able to run multiple tests and in a short time. So flexibility is the special feature. Now we move to La Spezia, where the maximum test power is increased up to 18 megawatt, and also the maximum flow rate up to 65,000 cubic meter per hour. The special feature is the capability to test a large pump in full scale, and also the possibility to run, for example, boiler feed pump at the plant temperature. Basically, we have a high temperature loop able to run up to 200 degrees C. Last but not least, there is the test center in Fresno, California, where the maximum test power is up to 2.5 megawatt. The maximum flow rate is 7,500 cubic meter per hour, And here the special feature is the capacity to test hydrogrit grit removal. That is a very special machine, and we are able to test in our facility. Okay, thank you. Now move to Simon.
All right, thanks, Massimiliano. So we're going to talk a little bit now about, go a little bit deeper into the test standards and try and highlight certain kind of key things that you should really pay attention to. So next slide. So we talked about this earlier, that no pumps are not digital machines. No pump test is identical. You can, with certain controls, manufacturing controls, reduce the scatter that you get, but you can never eliminate it. That's just the nature of manufacturing. There are times when you do want to reduce that scatter. For example, if you have operating pumps in parallel where you need to match the performance very closely, for example, for the reliability of the system. There's other times when it makes less sense when it's, say, an intermittent pump, and a single fire pump, for example, where you don't really need to worry as much about it. So that's one of the considerations there, where as you prescribe tighter and tighter test tolerances, now the manufacturer has to apply better methods, better controls, and of course all of that costs money, as we've talked about. The graphic just shows a typical pump with a whole bunch of tests against it, and you can see that's pretty much as expected for sort of an average manufacturer, the kind of scatter that you would get, just to kind of set the stage. Next slide. Okay, so this is a really important point, is when you're first setting up your project and you're comparing vendors, it is critically important that when you're comparing the vendors, that the vendors are applying the same test tolerance. It can well be the case that one vendor will quote a certain test tolerance and different vendors will quote something else. That causes, as you'll see later on, a lot of difficulties in understanding which vendor is best, what you're actually going to get in terms of field performance. So, defining the appropriate test standard really should come from the end user based on what value they have, what values they need to achieve in the field. The graphic shows why, and that is that the vast majority of a pump life cycle cost is not the purchase of the machine. The purchase of the machine is only around 10-12% of the total life cycle cost. The vast majority of it is energy consumption, pump maintenance, pump operations. So, when we look at that and you say, okay, if I'm concerned about how much I'm going to spend over the lifespan of this machine, it's really important that I look at how much I'm going to spend on energy consumption, how much I'm going to spend on maintenance, things like this, and that then drives the testing that I'm going to want to specify and the tolerances that I want to apply. Next slide. Okay. So, careful what you ask for. We talked about there's a number of test standards: API 610, HI 14.6, ISO 9906, and there are some others that we didn't mention here. The standard has a huge impact on the pump selection. It's really important that you get the pump OEMs quoting to a consistent set of testing and test tolerances, so that you're able to compare the offerings consistently. That said, you don't want to specify a requirement that is more than you need, because it is going to cost additional lead time and additional cost in your purchasing. So, for example, a low energy intermittent pump, as was mentioned there, efficiency is not such a big deal for that over the lifespan of the pump, and you probably wouldn't be as worried about that. On the hand, if you have a high energy consumption process with a high power pump and it's running continuously, not specifying the right test tolerances are literally going to cost you millions over the lifespan of that equipment. And it is very important in those cases that you know exactly how your pump is going to perform on the test stand, and that you have the appropriate tolerances applied. Next slide. Okay, so let's kind of dig into the tolerances a little bit. We pulled the tables, or I pulled the tables from both HI 14.6 and API 610. So the immediate thing that you can kind of see is HI has a whole bunch of different test tolerances, and it's like an alphabet soup. There's 1B, 1E, 1U, 2B, 2U, and 3B. A lot of different ones. Whereas with API 610, you get one set of test tolerances, and that's it. And the reason for this is that API 610 historically was focused on consistency and reliability. By default, API does not control for efficiency. That was not something they were considering. They do control for rated power, but that's mainly to ensure you don't overload the motor. They were never historically interested in efficiency. On the flip side, some of the HI tolerances are very much focused on efficiency, as you'll see later. The second takeaway is that over the years, the standards have tried to align. HI 14.6 grade 1B is notionally equivalent to API 610. However, API 610 has additional requirements for controlling shutoff head, which 14.6 does not have. One standard is not necessarily better than the other. It really depends on your end goals and what you're trying to achieve, as we'll see a little bit later. But there's trade-offs in using either of these standards. So let's go on to the next one. Okay, so let's take some practical examples here. So this one's I won't say silly, but it's an example just to highlight a point. That's so we're going to take here an example of a pump where the purchaser specified HI 14.6 grade 2B, and what does that practically mean? Well, we've plotted it out here on the graphic on the right hand side. So if we take each of these in turn, the head flow characteristic, which is the light blue, the middle light blue line, has to pass through one of the red lines that correspond to the head and flow tolerance, which in this case is plus or minus 5% of head or plus or minus 8% of flow. So the two dotted lines that exist either side of the head flow characteristic, they show you the extent to which that pump could vary on the test stand and still be acceptable. This tolerance standard also allows the efficiency to be up to 5% below what the characteristic of the pump sold was, and that is shown by the red line. The red line at the top of the graph there that says minus 5%. So the efficiency curve must pass through that vertical red line, representing the efficiency tolerance. And if efficiency was important to you, what that means in practicality is that this pump could test 5% low in efficiency, and for a 1 megawatt pump, that's with European energy prices, that's about 2 million euros more that pump is going to cost you over its lifespan, which is quite a lot, and most likely more than you actually paid originally for the pump. So let's go to the next slide. Okay, so here's a counter to that. This is an example with HI 14.6 grade 1U, which is commonly specified by end users or purchasers of pumps where they are very concerned about attaining the highest possible efficiency. And in this case, the setup of the allowable tolerances is quite different. So for the head and flow characteristic, you're only allowed a positive tolerance. So either up to plus 6% on head and up to 10% on flow. You are not allowed any negative tolerance on efficiency at all. So the efficiency that the pump demonstrates on test must be at least as good as what was sold, if not slightly better. And you say, well, that's great. That's fantastic. Why not specify this all the time? Well, in addition to the cost to the manufacturer of making sure that it hits that, there is another consideration that we have here. We do want to specify it when the pump efficiency is critical, but pump efficiency does not equal system efficiency. And as you can see on the graphic, when I specify 1U, it's quite likely that my head and flow is going to be higher than the notional sales curve, and also my power is going to be higher. Now, if you can handle that additional head and flow going through your system, if you can handle it in an efficient way, then great. You can specify 1U and you're good to go. But if all you're going to do is essentially take that energy that the pump has put into the fluid and then break it down across some pressure control valve, you've essentially put a lot of energy efficiently into the fluid for no benefit. So it is very important that you consider both, if you're targeting ultimate efficiency, that you specify the right grade for the pump, but also that your system can handle it in an appropriate way. Otherwise, it's, as I said, you're kind of wasting your time here a little bit. Next slide, please. So some other things to consider. What testing can and cannot do. As we showed, earlier, the same pump, depending on the tolerances that you apply, can pass or fail, because the allowable tolerances for the head and flow, the power, and the efficiency are different for each of these. When you test pumps, it isn't without some risk. I'll say I routinely get customers who want to run pumps that are absorbing 2, 3, 4, or even higher megawatts of power, and they want to see these run at zero flow. That's generally not a good thing. And thankfully, the standards, particularly API, have started to kind of provide guidance of why that isn't a good thing, for the reasons that I mentioned earlier, that you're essentially putting 2, 3, 4 megawatts of energy into some fluid that's sitting inside the pump, and very quickly it can overheat and cause damage to the pump. Similarly, if you're specifying a pump for handling something other than water, particularly like light hydrocarbons, it's going to be tested on water. The amount of power that the pump absorbs is essentially directly proportional to the density of the fluid. So if your fluid that you're pumping has a specific gravity of 0.5, on the test stand with water, it's going to absorb twice the energy. That can be a problem in terms of it also will generate more pressure. So that can be a problem in terms of the exceeding the pressure boundary limitations of the pump. It can be a problem in terms of exceeding the maximum power the pump can absorb. And that requires a specific discussion with the OEM about how to test that pump safely. Another requirement that unfortunately we see quite a lot is a request to strip and inspect the pump after the test. And I'll be honest, I just think it's generally a terrible idea. It's essentially like striking a match to see if it lights. You've taken a pump that you've proven to be good, and then you're going to take it apart and put it back together again. And now what? you've just put the pump back together. Are you going to test it again? What are you going to do? So it's generally not recommended to do that. Although there are some disassembly things like checking bearings, plain bearings, that are okay to do. Finally, some some things that testing doesn't cover. It doesn't validate a performance test does not validate the pump package. For that, you would have to specify a full train test. Factory testing does not guarantee success at site. A factory test setup is going to be optimal. There are quite prescriptive requirements on how we do the piping, instrumentation, all this kind of stuff. When you go to site, you have the impact of the fluid, the quality of the installation, and upstream and downstream factors, of which there are an almost infinite number. So all of these things can impact it. Next slide. All right, so special testing. Kind of mentioned this earlier. If you have a low SG fluid, you have to do some special things. We talked about it earlier in Hydrotest. You may need to add a wetting agent, something that allows you to essentially better simulate the leakage capabilities of the fluid that you have at site. Power limits need to be considered. As I mentioned, vibration can be misleading because now you're putting much more power into the pump than you would be at site. So that again needs to be a discussion between the purchaser and the OEM about how vibration is going to be measured and how it's going to be kind of recognized whether something is acceptable or not. This is particularly the case because sometimes you have to run it at a different speed, and then it gets quite interesting. And NPSH testing isn't necessarily representative. Testing of water is usually more pessimistic than what you will see running with a light hydrocarbon due to the thermodynamic effect. So again, something to consider. Although generally the water test is going to be, if it tests on water fine, it's going to be fine in the field. Finally, an example on high temperature testing. Massimiliano mentioned this earlier. There are some times where we need to test at high temperature to validate that the pump performs acceptably in terms of handling that high temperature, in terms of thermal expansion, in terms of thermal shock. And there aren't that many test loops that can do this. We do have one of those. Next slide. And then finally, factory versus field testing. I saw a question of this in the chat. Factory testing should always be the first choice. You have a control conditions, you have full calibrated instruments to the levels that you need to, and you can control the variability to the levels that are required within the test standard. As soon as you go to field tests, your instruments are probably not good enough. Your piping may not be good enough. So you, at the very least, you're likely to have to install some better quality instrumentation for that field testing. In my experience, you have issues around piping, which may not be as good as you would like. You have limits in terms of they're usually trying to operate the thing at the same time. You may not be able to get to all the flow rates that you're looking for, and the costs are very high because you have to mobilize people to go out there and sit and wait for the right conditions to occur to measure the pump. It can be done. It needs to be very carefully discussed, and it is not cheap. It's not cheap, and it's not easy to do. It's the experience that I've had in the times that we've had to do it. So factory testing should be the default. It has a lot of value when you specify the right tests, and you should always use that as unless there is no other option. Okay, I think we're done there, Sam.
Yeah, perfect. Thank you, Simon. Thank you, Massimiliano. Just a quick last reminder for any questions, anything anyone wants to ask. I appreciate we have already had some in. Just 2 more slides, and then we'll get on to the open Q&A. So just a quick note here on what to watch for. As an end user coming into a site, what are some of the key bullets? Obviously, we could spend a lot more time on this, as with just about any section we've covered. We just want to talk about some of the key factors. The number one at the top here, it's it's hard to explain how often this is not understood and aligned. And this is very often because the people that specify the equipment are not the people that are coming in to inspect the pump on test. So it's very important, especially if you're using a third-party inspector, that they are exceptionally clear on the test procedure that's agreed. So it's not going to be like the last test they saw. It's going to be how many tests, what's been agreed, what data points have been signed up for, and above all else, what's the pass and fail criteria. Because as we've talked about, you can have a huge miss on test and it still be completely acceptable within the tolerance. And that feels very uneasy to everyone involved, but it's something that people need to understand going in, solves so much confusion and back and forth after the event. It's often also particularly when addendums to specifications have been added, this is typically the point that everyone realizes those addendums are not always as clear, because things that were not maybe given the scrutiny at the upfront stage then become suddenly very, very real when we're trying to evaluate against a test. From a practical point of view, in terms of reviewing the test setup, you should always walk the test setup, go around with the OEM, do a visual check, make sure there's a sensible number of straight lengths in front of and after the pump, check where they're taking pressure measurements, check where they're taking flow measurements. These things are very, very important. It's also your only chance to visually check that the equipment is free of leaks, contamination before the thing started. And we're running a little bit behind time, so I'm not going into too much detail on the rest. But just two key points. Check the instrument calibration for key instruments, which is predominantly your flow meters. You're not going to check every bit of instrumentation on the test rig, but you do want to check the calibration there. And finally, understand curve fit. So what you see in the curves that we've shown all the way through are a line of best fit, and that is what the pass or fail criteria is aligned to. But you want to see the raw data against that aligned curve. You want to make sure that no one's taking liberties with how that curve fit has been done. And that is a very, very key part of the process. Okay, the last slide before the Q&A is just a very quick wrap up. So from summary, hopefully we've got across why it matters. Ultimately, it costs a phenomenal amount of money, both in terms of lost energy, if we're not understanding the test tolerances, and in terms of fixing any issues at site. So testing is of critical importance. The right level of testing is of critical importance, and specifying more if the system or process can't handle it is detrimental overall. Given a quick overview of the different types of pump tests and standards, we've talked about the risks predominantly around different fluid types, the fact that you're not on the same foundation, you're not doing what we would call a full string test or a full complete unit test. Talked about some of the impact on light hydrocarbons, how that affects NPSH, how it can also affect the risks of running back towards closed valve or zero flow. And we've talked about the test setup limitations and factory and field testing. And we finally just had a very quick run through from an end user. But the core takeaway of this, testing is incredibly important, it's incredibly valuable, but it's also complex. And this only really succeeds when there's a lot of collaboration between end user, purchaser, and the pump OEM. And with all these things, it's that collaboration of the pump OEM doesn't always understand what the end user needs. And equally, the EPC is stuck in the middle trying to balance all these requirements. It's only through open dialogue that these things can get fixed and rectified. What we are dealing with as a group is a complex interaction within a bigger system. And the pump is one tiny part of that. And it's our role to help try and provide honest, transparent guidance to make sure that we can make sure our piece is doing its weight within the overall system. So with that, we're going to go to the Q&A. We've just got 4 minutes and we want to make sure we are conscious of everyone's time. So the first question that came in was from Michael. So Michael, you've asked some specific questions regarding pump testing at site, which we will get back to you outside of this, just in terms of specific brands of flow meters and torque meters at site. But one of your other points was you mentioned that is a degradation of efficiency of 1% every year practical? I'm going to give you the worst answer. Please reach out if you want to discuss it in more specific terms. But the answer is it depends. If you have a clean product running at slow speed, you absolutely should not lose 1% of efficiency a year. If you're on an incredibly abrasive service at 6,000 plus RPM, you are going to see losses in that sort of ballpark. 1% a year is very aggressive. And it really comes down to the speed the pump's operating at and how unclean or how much contamination is within the process fluid. So if there's any specific applications you want to talk through, please do reach out. Myself, Massimiliano, Simon, we are all available on LinkedIn. In regard to your other points, we will get you a response outside of this session, just because in 3 minutes, we're not going to be able to go through the specific type of instrumentation. Suato's asked a question that I'll hand to Massimiliano.
Yeah,
so during the hydro test, when the temperature drops, so the ambient temperature drops, what is the tolerance of pressure drop from a pump perspective, and is there any standard we can use?
Okay. The recommendation here, the standard to be used is API 610. What is written in the standard is that no pressure drop is allowed. The practical way is that some stabilization of the fluid is generally there, and some basically accuracy of the instrumentation has to be considered. This is the practical recommendation, but you have to be sure that the pressure drop is not due to any leak. And the other main recommendation is that not to have a huge drop of temperature during the hydro test. This is the quick aspect.
Perfect, thank you, Massimiliano. We've got one from Abhinesh has come in, which Simon, if you're okay to cover. So do all pumps offered by Trillium come with performance testing as default, or does it need to be specified?
I mean, so if you're buying an API 610 pump, that certain testing is mandated in that standard. Okay, so your performance test has to happen. Other tests beyond that, you have to specify. They're optional tests. So, for example, an NPSH test or a mechanical run test or anything like that. These are optional tests. They're and you need to call out those on the data sheet. I should say also the hydro test is mandatory as well. In terms of HI 14.6, I mean, essentially, once you're outside of that, if you're going to some other industrial standard that governs ANSI or ISO pumps, they do mandate certain testing. It is very, very limited in my experience. So generally, the safe answer would be that you would need to specify it.
Okay, perfect. Thank you, Simon. So last question, there's been quite a few that we're not going to be able to get to that we will reply to. So with the email address you've supplied to this, we'll be able to get back to you outside of the event. So apologies for those we haven't got to. We just have one more from John that's come in, which Massimiliano, I'll let you cover. So would Trillium smart condition monitoring for pumps, so the Cyclops 2, be a potential solution for this? And what are the pros and cons?
Yes, basically it is on-site condition monitoring. It is basically a wireless system that is useful to monitor real time the performance of the machine. It is connected to a cloud, and from the cloud we can basically read the main parameters. This is the very quick answer. If you need additional information, basically we have brochure, we have everything about that.
Yeah, that's great. Thank you, and apologies to those that have submitted questions that we've not got to. We will reply to you directly after this. So thank you very much for everyone's time. If you have any other questions, any other follow-up, again, reach out to myself, Simon, Massimiliano via LinkedIn. We are all readily contactable. Other than that, it's just say thank you very much for your time. We want to be respectful and make sure we finish pretty much to schedule. So thank you all very much. Thank you, Simon. Thank you, Massimiliano.
Thanks.
Thank you.